A problem that is out of sight and out of mind does not get fixed. With this being the case, many people go right through their science textbooks and don't see any of the problems that are in them. Thereby, they don't get fixed. We are here to remedy that.
As many can attest, when you join the Censored Earth community, you are given a new set of eyes. Now, I've studied Earth science before, but now that I've been given a new set of eyes, I'm going to go back and take another look and tell you what I see.
This is Modern Earth Science Destroyed, Chapter 2.2, The Movements of the Earth.
I have a sincere desire to fortify my education from the ground up. In order to do that, I need to point out and acknowledge the holes in my education.
What do you mean by holes?
When a concept is taught that doesn't have any observations to support it, that is what I call a hole.
So when we are blindly taught something without any grounds to support it, and someone comes along and says we were taught wrong, how could we tell them otherwise, especially when they have evidence to support their claim?
That is what we want to fix.
We want something better than saying, this is true because my textbook said so. That is committing the genetic fallacy.
Since fallacies can't support anything, unsupported concepts fall to the ground and crumble. So our goal here is to point out the holes where we see them, so people can try and defend the book and support the concepts it teaches, or let them fall and allow them to be replaced by better supported concepts.
Alright, let's get searching. Movements of the Earth.
The Earth is constantly in motion. You are traveling with the Earth around the Sun at an average speed of 106,000 kilometers an hour.
Wow, we didn't have to look very far before we found our first hole. What observations tell us the Earth is traveling around the Sun at 106,000 miles an hour? Where does that number come from?
Kerplum?
If this is an introduction to Earth science, I've got to ask, why are they starting with a conclusion? It's like they're trying to build the roof before they build the foundation.
The movement of the Earth around the Sun is called revolution. Each complete revolution takes 365.24 days, or 1 year. As it revolves around the Sun, the Earth also spins on its axis. This spinning motion is called rotation. Each complete rotation takes about 24 hours or 1 day.
Uh-oh, it looks like we have some floating concepts here. What observations tell us the Earth revolves around the Sun? What observations tell us the Earth is spinning? Let's see if they can provide some support for their claims. The rotating Earth, that sounds promising.
For everyone on Earth, the most observable effects of the Earth's rotation on its axis are day and night. As the Earth rotates from west to east, the Sun appears to rise in the east in the morning, it travels across the sky, and sets in the west. At any given moment, it is daytime on the hemisphere of the Earth facing the Sun. It is nighttime on the hemisphere of the Earth facing away from the Sun.
Alright, so here we actually have two observations. I can accept that. Now we can acknowledge the spinning Earth concept as a hypothesis. But that hypothesis, which describes the heliocentric concept, has a rivaling hypothesis that describes the geocentric concept. Please notice how both are supported by the exact same observations. Since both hypotheses are supported by the same observations, we're going to need some additional observations in order to prove one way or the other.
So, what additional observations would confirm or disconfirm one hypothesis or the other?
How about this? If the Earth were spinning at about 1,000 miles per hour, shouldn't the momentum push things outward? Wouldn't that cause most of the standing water on Earth to tilt toward the equator to some degree or another? When that doesn't happen, we can call that confirming evidence supporting the geocentric hypothesis that says it is the Sun that moves around the Earth.
We can also call that disconfirming evidence for the heliocentric model. So with that, it looks like our textbook's rivaling hypothesis has a stronger foundation and takes the lead. If anyone would like to argue against this, or try and provide additional evidence for the claim that the Earth spins, please feel free to come and visit our debate board. There's a link in this video's description.
The revolving Earth.
The Earth's orbit, or path around the Sun, is slightly elliptical, or oval-shaped. Therefore, the Earth is not always the same distance from the Sun.
Oh dear, I see a floating concept. How do they know the Earth has an elliptical path around the Sun?
Kerplunk.
152 million minus 147 million? That is a 5 million kilometer difference. I think that's a little more than slightly elliptical. I'm curious, how do they determine the Earth's distance from the Sun in the first place? I don't see the book explaining that anywhere. After so many answers have been given throughout history, it would be nice to know what methods each person used and where they got their numbers from.
At its closest point to the Sun, the Earth is said to be at perihelion. At its farthest point, the Earth is at aphelion. As shown in Figure 2-6, the Earth reaches perihelion on January 3rd and aphelion on July 4th. The Earth's aphelion distance is 152 million kilometers. Its perihelion distance is 147 million kilometers. The average distance between the Earth and the Sun is 150 million kilometers.
Hey, look at that! They agree with us that the Sun is not 93 million miles away. 150 million kilometers does not convert to 93 million miles. Oh, but there's still a whole bunch of floating concepts here. Where are all these numbers coming from, and how do they claim to know all these things?
Kerplunk! They are not explaining any of their reasoning.
I wonder what they call this place between the aphelion and perihelion. Mid-helion, perhaps?
I don't know, but we could call it that. I'm also really curious as to why they claim the Earth has an elliptical orbit and how that would work. An object should travel in a circular path when there is a balance of forces. But when you get an imbalance of forces, that is when you would get an elliptical path. So what is causing the imbalance here? Does someone claim that the attracting forces are stronger on one side of the Sun than they are on the other? Or does someone claim that the Sun is wobbling back and forth as the Earth orbits around it? When it comes to ellipses, the picture of a skateboarder on a half-pipe comes to my mind. In this, the skateboarder would travel in an elliptical path across the half-pipe due to the imbalance of forces acting on him. Now what really catches my attention here is the peak of each side of this elliptical path. When the skateboarder goes up and turns around, there is a brief moment of weightlessness. This is how zero-G planes work. So if the Earth is traveling in an elliptical orbit, the entire Earth should experience a change in weight throughout the year. Please also keep in mind how when the skateboarders hit the bottom of the half-pipe, they suddenly feel an increase in the G-force acting on them.
As gravity pulls snowboarders down the half-pipe, they gain speed. But at the very same time, they're being pushed against the sides of the half-pipe by contact forces from the surface of the snow.
That snowboarder feels like they're being crushed against the surface.
Even 2006 gold medalist Shaun White has felt the power that friction can exert on his board.
There's actually like G-force when you're going up and it's sucking you against the wall.
So at some point in its elliptical orbit, the entire Earth should experience some kind of gravitational variation. But we don't feel that. That stands as disconfirming evidence to the claim that the Earth travels in elliptical orbit around the Sun.
And shouldn't we all be lighter during the daytime than we are in the nighttime?
We are lighter when the sun is shining on us. I'm as light can get. You've seen me in the sun, being a redhead and all.
That's true, but that's not what I'm talking about. I mean, we should all weigh less during the daytime than in the nighttime.
Okay. Weight-wise, not light-wise.
Yeah. That is another disconfirming evidence for you, against the claim that the Earth is even orbiting the Sun. Another thing I am deeply wondering about is this. An object in motion should stay in motion unless met by an equal opposing force. In which case, the object would come to a complete stop. But if the opposing force is greater, then the object should turn around and start moving in the other direction. So, in an elliptical orbit, in order to make an object turn around, it'll take a greater force to make it do so. What is this greater force? Why would the attracting forces suddenly get stronger when the Earth is at its farthest distance from the Sun?
That seems to be contradicting what the book said in the last lesson, which said gravity is supposed to be weaker when it is farther away from its gravitational source. Let's think about the force that causes our skateboarder to turn around while in mid-air. While in the air, he doesn't instantaneously turn around, but gradually slows down and then turns around. With that observation, the force acting on him can be seen like a current pushing him back. And thinking back to our last lesson, that makes me think of a magnetic current. In which case, if gravity is an electromagnetic current, shouldn't there be a north pole and a south pole? And if the current is attracting on this end, shouldn't there be somewhere else where it is repelling things away from the Earth?
I can't say I'm aware of any places like that.
Anyway, we are still back to why would it take the Earth more time to turn around on one side of the Sun than the other? The book doesn't offer any answers to that.
Perhaps someone else can answer that. Until then, their concept is a pile of rubble that desperately needs support.
Okay, let's move on. New page.
As shown in Figure 2-7, the Earth's orbit lies in a plane. The Earth's axis is tilted 23.5 degrees from the perpendicular 90 degrees to the plane of its orbit.
Yeah, an elliptical orbit on a flat solar plane doesn't make any sense to me, unless the sun were wobbling for some unknown reason. If the book's aim was to make students curious, I'll give them points for that. But what they lack is a direction as to where to apply that curiosity.
As the Earth revolves around the Sun, the direction of its axis points does not change. It always points toward the North Star. Consequently, during each revolution, the North Pole tilts at times toward the Sun, and other times away from it. When the North Pole is tilted toward the Sun, the Northern Hemisphere has longer periods of daylight. When the North Pole is tilted away from the Sun, the Southern Hemisphere has longer periods of daylight. The Sun's rays are nearly parallel to one another as they reach the Earth. Because the Earth's surface is curved, however, the Sun's rays strike different parts of the Earth at different angles. The amount of solar heat an area receives depends on the angle which the Sun's rays strike the area of the Earth's surface. When the Sun is directly overhead, its rays strike the Earth at a 90-degree angle. The closer to 90 degrees the rays are, the more concentrated they are, and the greater is the heat they produce on the Earth's surface. Where the rays spread out from 90 degrees, the solar heat reaching the surface of the Earth becomes less concentrated.
Huh. I don't see how changing the angle of the Earth's surface would make parallel rays any more or less concentrated. Changing the angle at which they are received isn't going to change the distance between the beams mid-flight.
The angle at which the Sun's rays strike each part of the Earth's surface changes as the Earth moves through its orbit. When the North Pole is tilted toward the Sun's rays strike the Northern Hemisphere at higher angles. When the North Pole is tilted away from the Sun's rays strike the Southern Hemisphere at higher angles.
The seasons.
Changes in the angle at which the Sun's rays strike the Earth's surface and changes in the amount of daylight cause the seasons. For example, when the North Pole is tilted away from the Sun, the angle of the Sun's rays falling on the Northern Hemisphere is lower. As a result, there are fewer hours of daylight. The weak rays of the Sun and the short hours of daylight produce the cool winter season in the Northern Hemisphere, At the same time, the angle of the sun's rays striking the southern hemisphere is higher, and there are more hours of daylight. The sun's strong rays and the longer hours of daylight produce the warm summer season there.
So they're claiming the seasons are merely caused by the angle at which the sun's rays strike the Earth. They're saying it has nothing to do with how near or far the sun is from the Earth. Please take notice here of how when the Earth is at its greatest distance from the sun, that is during the northern hemisphere's summer. And when the Earth is closest to the sun, that is during the northern hemisphere's winter.
So when you're shivering to death outside, just remember, the textbook says that you're closer to the sun now than you were in the middle of the summer.
152 minus 147, that is a 5 million mile difference. And yet they are claiming the angles are condensing the sun's rays to make things warmer when the Earth is at its farthest point away from the sun. Sorry, I don't buy that at all. At the very least, I would expect the entire Earth to be warmer when it is closer to the sun and colder when it is farthest away from the sun.
I totally agree with you there.
Summer and winter solstices.
Because of the Earth's orbit, each year on June 21st or 22nd, the North Pole tilts toward the sun. On this day, the sun's rays strike the Earth at a 90-degree angle along the Tropic of Cancer. This day is called the summer solstice. It marks the beginning of summer in the northern hemisphere. Solstice means sunstop and refers to the fact in the northern hemisphere the sun follows its highest path across the sky on that day. Figure 2-8 shows this path as it appears in the northern hemisphere at the summer solstice. The northern hemisphere has the most hours of daylight at the summer solstice. The farther north of the equator you are, the longer the period of daylight you have. North of the Arctic Circle, there are 24 hours of weak daylight at the summer solstice. At the other extreme, south of the Antarctic Circle, there are 24 hours of darkness. By December, the Earth is halfway through its orbit, and the North Pole tilts away from the sun. On December 21st or 22nd, the sun's rays strike the Earth at a 90-degree angle along the Tropic of Capricorn. This day is called the winter solstice. It marks the beginning of winter in the northern hemisphere. At winter solstice, the northern hemisphere has the fewest daylight hours. The sun follows its lowest path across the sky, as figure 2-8 shows. Places north of the Arctic Circle have 24 hours of darkness. Those south of the Antarctic Circle have 24 hours of daylight.
Looking at this picture, I want to point out here how the three suns show the sun's position in the sky at solar noon in June, March, and December. This is what that looks like when you look at the sun's location at the exact same time on different days throughout the entire year, instead of just those 3 time periods. This is called an analemma, and it shows evidence that the sun appears to move at different speeds throughout the year. The sun reaches the very top of the analemma on June 20th, which is our summer solstice. It reaches the bottom of the analemma on December 20th, which is our winter solstice. And it hits that intersection once around April 15th and a second time around August 31st. So this is showing the sun at its highest point in the sky on each of those days. But if it were showing the sun at the exact same time in each of those time periods, then they would have to show 4 suns instead of 3 suns.
Yeah, good job at noticing that.
On another note, you might find it interesting to know that the moon also produces an analemma, but it completes a circuit once a month rather than once a year like the sun does.
That is pretty interesting. I think it's also pretty interesting how neither one overlaps in the center of the figure 8. For some reason, I think one would expect it to be in the center if the Earth were a globe. With it not being in the center, it seems out of balance.
Yeah, I can see that. It also seems a lot wider on the bottom than it is on the top. That is a for sure indicator that the sun and moon travel at different speeds throughout the year.
I agree. That seems to indicate 15 degrees per hour has some variation in it.
Autumnal and vernal equinoxes.
On September 22nd or 23rd of each year, the sun's rays strike the Earth at a 90-degree angle along the equator. This day is called the autumnal equinox and marks the beginning of the fall season in the northern hemisphere. Equinox means equal night and refers to the fact that the hours of daylight and darkness are equal everywhere on Earth on that day. The hours of daylight and darkness are equal because at the equinox, the North Pole tilts neither toward nor away from the sun. This position of the North Pole in relation to the sun is illustrated in figure 2-9. On March 21st or 22nd, the sun's rays again strike the Earth at a 90-degree angle along the equator. This day is called the vernal equinox and marks the beginning of spring in the northern hemisphere. As during the autumnal equinox, the hours of daylight and darkness are equal everywhere on Earth. On this day, the North Pole tilts neither toward nor away from the sun.
Precession.
The illustration in figure 2-9 also shows that as the Earth completes its revolution of the sun, its axis of rotation continuously points toward Polaris, the North Star. This has not always been the case, however. As the Earth rotates about its axis, the direction in which the axis points slowly changes in relation to the distant stars. This change results from a circular motion of the Earth's axis called precession. Precession is caused by forces acting on a spinning body. In this case, by the gravitational pull exerted on the rotating Earth by the Moon, the Sun, and the other planets. Precession causes the Earth's axis to move slowly in a circle, much like a top does as it spins on a table.
Comparing it to a top is interesting. However, the forces at work in the top are the top's momentum and the Earth's attracting forces pulling it downward. On a heliocentric plane, I wonder how they claim all the other planets create this downward force without knocking the Earth out of line with the rest of the plane.
The Earth's axis, however, completes only one full circle every 26,000 years, so Polaris will continue to be our North Star for many years to come.
And there is another floating concept for us. Where is that number coming from? Time zones.
Using the sun as the basis for measuring time, 12 o'clock noon is defined as the time when the sun is highest in the sky. Because of the sun's apparent movement from east to west, the sun appears highest over different locations at different times. For example, assume the sun is highest over New York City at 12 o'clock noon. In Philadelphia, a short distance west of New York City, the sun would appear highest a few minutes later. In Baltimore, just west of Philadelphia, the sun would appear highest a few minutes after that. If these communities were to set their clocks precisely by the sun, the clocks in each community would mark slightly different times. To avoid problems created by different local times, the Earth's surface is divided into 24 standard time zones.
Wait, what? Okay, so to avoid problems by different local times, let's create a bunch of different time zones so we can have a bunch of different local times. Yeah, I think China did a better job of solving that problem. Their entire country, which is comparable to the US in size, just has a single time zone.
In each zone, noon is set as the time when the sun is highest over the center of that zone. I'm sorry. The sun sure seems to be doing some pretty squampy things in some of these different zones. Because the Earth is nearly spherical, its circumference equals 360 degrees. Dividing 360 degrees by the 24 hours needed for one rotation, you find that the Earth rotates at a rate of 15 degrees each hour. Therefore, each of the Earth's 24 standard time zones covers about 15 degrees.
Exactly. Those time zones do not look uniform to me.
The time in each zone is 1 hour earlier than the time in the zone to its east. Unless you live in Alaska. Here's a time zone map from timeanddate.com. Let's go. This is the time in Fairbanks, Alaska. About 2 o'clock. Jump over into Canada. 4 o'clock. That's a 2-hour difference. We can see the same thing as we go around China over here. Here we are in Kazakhstan, right outside the border of China. We jump over. 7 o'clock.
Time zones are pretty messed up. It seems the textbook is quite wrong here in claiming time zones are determined by the sun moving at 15 degrees per hour.
Figure 2-10 shows the standard time zones in the United States. At 6 p.m. in New York City, what time is it in Los Angeles? In Denver?
This book isn't that old. It was published in 2002, but I think it is interesting how these time zones don't seem to match up with the ones we see on timeanddate.com. If the time zones were determined by the movements of the sun, I don't think they should be changing around as much as they do.
There are 24 standard time zones and 24 hours in a day, but there must be some point on the Earth's surface where the date changes from one day to the next. To prevent confusion, the International Dateline has been established. The International Dateline is a line running from north to south through the Pacific Ocean. When it is 8 a.m. Friday west of the International Dateline, it is 8 a.m. Thursday east of the line. The line is drawn so that it does not cut through islands and continents in the Pacific Ocean. Thus, the people living in one country have the same date. Note how this is done between Alaska and Siberia in figure 2-10.
Those sure are some crazy time zones going on over there. That looks like a 3-hour time jump.
During the summer, most of the United States uses daylight saving time. Under this system, clocks are set 1 hour ahead of standard time in April, which provides an additional hour of daylight during the evening. For example, if the sun sets at 7 p.m. standard time, it would set at 8 p.m. daylight saving time. In October, clocks are set back 1 hour, returning to standard time.
Thank you for watching.